gonna talk about decoding superheated steam from tables to turbines. First thing, we're gonna talk about what is a superheated steam. Okay, it's a thermodynamic related topic, so it's gonna be a little confusing, but I will try my best to, you know, decoding it. Superheated steam is a steam at a temperature higher than its saturation temperature. What is a saturation temperature? Saturated temperature is a temperature that don't make the water or whatever the liquid is change its form. Okay, so where the liquid and have a certain temperature that doesn't change its form into gas or something like other things. This is what we call a saturation temperature, and of course at a given pressure. But when we increase this temperature, we will enter a new region called a saturated mixture. This saturated mixture, it's a mixture between this liquid and this vapor. It's become like a percentage of liquid and percentage of vapor when we increase the temperature like 100 Celsius or 101 Celsius to the water, and keep increasing till it's become a superheated vapor. In this condition, superheated region, pressure and temperature become fully independent variables. This is independence is the key of unique properties. One of the properties is 100 pure gas. This is the state. This is a 50-50 at this point is a 50-50 vapor and liquid. This is 100% liquid. This is 100% gas. Condition it's when the temperature become higher than the temperature saturated temperature. Key properties: pressure and temperature are independent. This is a very important things to remember. The language of steam, how it read in thermodynamic table. This is a little confusing if you read it in the first time, but when you read it more than one, you're gonna actually understanding is. Saturated tables and superheated tables are separate. Okay, this is the first thing we need to know, but they have both a similar things, like we're gonna talk about it right now. First thing and first difference is in the saturated region, pressure and temperature are linked. Unlike the superheated, it's not linked as we talk it. They are become independent. Pressure and temperature are linked. Knowing one determines the other. T saturated is equal to F of P. This equation we usually use it in the thermodynamic when we know the saturated table, when we know the liquid are using in the equation or in the problem is as saturated liquid and is not yet in the saturated mixture or in superheated. So this is only if saturated in the form of the saturated. Therefore, you only need one of them, T saturated or the pressure, to variable either P or T as we talk about it, to find all other properties. Unlike in the superheated, if we know one of them, it's not really helping. We need the temperature and the the pressure. We need this to specify the real internal energy and enthalpy and also the entropy of the of the table. If we have only the pressure or the temperature, it doesn't help that much. Unlocking the puzzle, the crossover getaway to the superheated region. The first row in the superheated steam table for any given pressure aligns perfectly with the properties dry saturated steam. In the same pressure, saturation, temperature, this is not coincidence. We're gonna talk about it. It's a deliberate transitional crossover. In this saturation steam table, we know the pressure is 1 megapascal, the temperature is 189 Celsius. We don't need to know about the Vg and internal energy in the gas, and we're gonna talk about the enthalpy the most. This is the most thing is important to us. The enthalpy is this searching of numbers, and enthalpy in the superheated steam table is the kind of same if you compare it. This is very concerning thing. Why? Because in the same T saturated in the same T saturated and pressure in in the superheated and the saturated, we have the same enthalpy. That's not this, يعني, not that same, but it's very similar. Why does this crossover exist? Define the boundary. It acts as a clear dividing line between the saturated and superheated worlds. If I think I have no, unfortunately, I don't have a real table of the thermodynamic. I didn't add it up. That's my mistake. But if you saw one, or to be more exact, if you have seen one, you gonna know there are step by step, okay, a step by step shape, or more to be exact, stairs. Yes, a stairs shape in this tables. This shape, that shape exactly, is separating the saturated and the superheated table, okay, in the thermodynamic. So this is what we call a boundary. Link the tables. It's seamlessly connect a single variable saturated table with the two variable superheated tables. Prevent redundancy. Redundancy. It ensures the saturation values stay in their own section, which means the saturated steam table doesn't go with the superheated steam table. They are separated. They are just separated between. They are a stairs shape that separate them from each other, keeping the data organized. Expected behavior: steam low and medium pressure. At low pressure, steam molecules are so far apart and interact weakly. In this condition, steam behaves very much like an ideal gas. Thermal expansion. Adding heat leads to large increase in specific volume in the V. High energy response, charge and temperature result in significant changes in enthalpy and entropy, which is we called S. Approximate relation. Ideal gas is delta H kinda equal, not really, but kinda, Cp times delta T. The unexpected twist, the high pressure puzzle. But when happens when the pressure becomes very high? But what happens when the pressure becomes very high? The steam table shows something strange. Properties like specific volume and enthalpy and entropy almost stop changing even with a large increase in temperature, and we will answer why. As we have in this shown figure, enthalpy and temperature are become a very, like, it's almost a line, but it's slowly increasing as we see in the end. When a medium pressure and increasing the temperature, the medium pressure becomes like a line, and when the low pressure is increasing very much, even higher than the very high pressure, this is why we say the temperature and pressure will work independently when they enter the superheated region. Explanation: molecular concentration at very high pressure, molecules are forced extremely close to each other, like this figure. Strong intermolecular attraction forcibly severely restrict their freedom of movement and expansion. Losses of expansion ability, adding heat no longer translated into significant increase in the distance between molecules, as we can see here. Even if we put a heat here, they can't escape, they can't release that heat to anywhere, or even to the boundaries. They just keep taking it. Nearly constant specific volumes, since the molecules are caged, like in this figure, and confined, the volume hardly changes. The coefficient of thermal expansion approaches zero. Explanation 2. There are two explanations, by the way. The vanishing phase line. And at extremely high pressure, superheated steam began to behave more like a compressed liquid. As we know, as we know, the liquid cannot be compressed. It's uncompressible liquid than a gas. Its properties defined by near incompressibility, like we just said, change only slightly with the temperature. The ultimate state, supercritical fluid. This have a very specific conditions. We will talk about it right now. One of the condition is the pressure need to become higher than 22.064 megapascal, and the temperature is higher than 374 Celsius. Behavior. What is behavior? There is no longer distant difference between the liquid and gas phases. The substance in the unique state where thermodynamic properties change smoothly and continuously. This is the critical point. This is the supercritical fluid region. This region is how much you increase the temperature or the pressure. It's only doesn't change the form of it. It's just become this. It can't escape this region. Only if you decrease the temperature or pressure, it will become a liquid again. Then so it become a gas again firstly, then a liquid. The modern engineer power generation and the Rankine cycle, superheated steam is used in Rankine cycle to dramatically increase the thermal efficiency of power plants. Increased efficiency. The higher the temperature of the steam entering the turbine, the more work can be extracted, increasing the cycle efficiency. Firstly, when the superheater give us the superheated steam, it will enter a turbine, which make it, spin around and give us the power we need. Then the superheated steam will excite the turbine, then go to the condenser and become a liquid again, then to the pump and go to the boiler, and the pump gonna pump that liquid again to the boiler, and it will increase the temperature, and by it will enter the superheater. This pump at the boiler, it's gonna change its form from liquid to gas, and from gas liquid to gas, and from gas to superheated steam, and it will enter the turbine. Turbine protection: the superheating ensures the steam remains gaseous state as it expands through the turbine. This prevents liquid water droplets from forming, which can cause catastrophic erosion of high-speed turbine blades, which will, cost a lot of money, because we need to replace these blades, and it's very, very expensive. The backbone of industry: turbines and heating. Application 1, and it is steam turbines. As we shown in this cycle is always become sorry this cycle is 90% used in steam turbines. The goal of its superheated steam is to maximize extracted work, and the method superheating provides the highest possible enthalpy for expansion, maximizing energy output while minimizing energy loss. Application number 2: industrial heating. As we can see, the superheated steam have two inputs, we can say it about that, and steam jacket, and this product steam superheated steam also enter from here, and a condensate that will, when the superheated steam excite, they will gonna turn it into liquid and rejoins again. The goal is to provide high and controllable process temperature. Method: superheated steam delivers high heat at a constant high temperature without needing to increase pressure, making the steam safer and more efficient than using insaturated steam at enormous pressures. As we seen in this, it's give us a high enthalpy with a very low pressure. Head to head saturated with superheated steam. This is just a simple comparable between them. Temperature equals saturation temperature. This temperature is higher than T saturated at the same pressure. Latent heat exits HFG, which HFG is exist because FG is meaning of fluid gas. So yeah, either way, in superheated steam, HFG is the enthalpy of fluid gas equals 0, because there are no fluid is remaining, it's only gas. Behavior of heating: phase change occurs liquid to vapor. This from sensible heat. This temperature rises. Even if we just keep increasing the temperature, it's only will become a sensible heat. This state is a mixture of liquid vapor or 100% dry saturated vapor. Superheated steam is 100% pure vapor. From coding to reality, a summary of this journey. In the end, the core summary is: the structure of a stream tables isn't arbitrary, it's a direct reflection of the underlying physics between molecules. The crossover region, I love to call it that, the boundary line also, and the strange stability of high pressure properties are natural consequences of minimizing molecular free energy and the disappearance of a gas-like behavior. Main conclusion, I hope you get the main conclusion of this. Understanding the deep link between data, physical theory, and material behavior is the essence of effective engineering, allowing us to design more efficient and reliable energy and manufacturing system. Lastly, key points to remember. The tables tells a story. Superheated steam tables use two independent variables, it's pressure and temperature, because they are independent, and the crossover is the bridge of the connects them to the world of saturated steam. Pressure change everything. At high pressure, molecular constant force steam behave more like a liquid, leading to stabilization its properties. With increasing temperature, superheating is the key to the efficiency in the power generation and industrial application. Superheating is used to increase work output, boost efficiency, and protect the vital equipment like turbine plates, and just like we said, in the end,